Alright, so in the second of our two videos on the Hadley Cell, we're going to cover a few assorted topics related to the Hadley Cell. Energy transport associated with the Hadley Cell, absolute angular momentum and how that gives rise to the subtropical jet, and variability within the Hadley Cell, particularly in terms of seasonal timescales. So we start again, as we did in the first video, with this depiction of the mean annual global insolation, how much solar radiation reaches to the Earth and its atmosphere, averaged throughout the course of the year. So again, we had about 400 to 500 watts per meter squared over the equator and tropical regions, and much less, on the order of 150 to 200 watts per meter squared in the polar regions. So of this amount that actually reaches to the Earth and its atmosphere, about 70% is absorbed by the atmosphere or the surface in the tropics. It has what we would call an albedo, a measure of its reflective ability, of about 0.3. And about 30% is absorbed by the atmosphere or the surface near to the poles. It has an albedo of about 0.7, which indicates very high reflective characteristics and capabilities of the snow and ice that dominate the polar regions. So if we input these to Stefan-Boltzmann's equation, which relates an amount of energy to the temperature, we can get estimates for the annually averaged atmospheric temperatures associated with the equatorial regions and the polar regions. If we do so, for the equatorial regions and the tropics, we get about 270 Kelvin. So keep in mind, these are averaged over a large depth of the atmosphere, not just specifically at the surface. And so this 270 Kelvin should not be inferred to be what you would expect to see a temperature at the surface to be near the equator. It's certainly much too cold to be that. Whereas if we do this for the polar regions, we get about 170 Kelvin. The actual difference is a little bit under 100 degrees Kelvin or 100 degrees Celsius, but it's very, very large and much larger than what is actually observed. In fact, this is 2 to 3 times larger than is what is actually observed in an annual mean basis. So that tells us that this picture of taking into account only the solar radiation that comes in from the sun to the Earth and its atmosphere, and how much of that is absorbed versus reflected or lost to space, that's an overly simplistic picture. We cannot use that alone to understand the difference in temperature between the tropics and the poles. There must be other things taking place. So we come to this depiction of meridional heat transport, and the big information that I'd like to convey with this is the net surplus of radiation here in the tropics and subtropics versus the deficit in the middle and higher latitudes, where the amount of outgoing radiation exceeds what is incoming, which would imply that from radiation principles alone, you would constantly be cooling near to the poles, and you would constantly be warming near to the equator, maintaining, if not growing, an even larger temperature difference between the equator and tropics and the polar regions. However, as this depiction indicates, there is heat transport that takes place in this meridional or north-south sense to help counteract that. Take this surplus of radiation and transfer it to higher latitudes. Reduce that surplus that is here, reduce the deficit that is found at higher latitudes. So there are many, many different types of energy transports that exist, and the Hadley Cell is one form of those energy transports. So we can break that total energy transport down into the sum of several different things. First one is mean transport by features like the Hadley Cell. And as you get to higher latitudes, this also includes things like the Ferrel Cell and the Polar Cell that you might have been introduced to prior to this class. In total, these features comprise about 30% of the total meridional energy transport across the globe when averaged over the course of a year. There's also transport by what we would call transient or short-lived mobile atmospheric eddies, such as mid-latitude and tropical cyclones. So all of our cold and warm frontal systems are trying to bring cold air to the south and warm air to the north to try to mitigate against this temperature difference that exists due to radiation. Tropical cyclones do the same as well. They originate in the tropics and carry warmth and moisture poleward with them as they evolve through their lifetimes, sometimes depositing it into the mid-latitudes or even higher into the polar latitudes. Those are about 40% in the annual average of the total meridional heat transport or energy transport more generally. Then there's also transport by stationary eddies, and the most common features of these are oceanic features, such as the Gulf Stream extending from the Gulf of Mexico around Florida and up the east coast of the United States, and the Kuroshio Current off of the coast of Japan and across the North Pacific. These are driven by atmospheric phenomena, such as the subtropical anticyclones that we've introduced before, but they are associated with oceanic transports. They too act to take warm waters poleward and on their backside bring cold waters from higher latitudes down toward the equator in the eastern portions of the ocean basins. These account for about 30% of the total energy or heat transport in the meridional direction as well. So for the Hadley cell, we're going to focus on this mean transport term. And in particular, in the tropics, the Hadley cell is responsible, and unfortunately this gets a little bit cut off by my picture here, but the Hadley cell is responsible for most tropical energy transport in the north-south direction. Yes, there are some characteristics related to tropical cyclones here. The ocean currents extend to the northern fringes of the tropics in some cases, but the bulk of the meridional or north-south energy transport in the tropics is accomplished by the Hadley cell. So let's take a look at a quantification of this energy transport or heat transport. And this is dating back to Ed Lorenz's work over 50 years ago now, but is still quite valid, quite relevant to us today. Along the x-axis of this diagram, we have latitude. We have the equator here at the center, 0 degrees latitude. Northern hemisphere is on to the left, southern hemisphere is on to the right here. The vertical axis is the transport, with values ranging from -50 to 0 to 50. This tells us the magnitude, but also the direction of the transport. Positive values are transport to the north in either hemisphere. So in the southern hemisphere, this would be toward the equator. In the northern hemisphere, this would be toward the North Pole. Negative values indicate transport to the south, which would be toward the equator in the northern hemisphere and toward the South Pole in the southern hemisphere. The total energy transport is given by this dark blue line that you see through here that I'm tracing with my laser pointer. There are 5 major transports that we can break the total transport down into. The purple lines the pink line indicates 3 separate terms. The atmospheric transport of sensible heat, the atmospheric transport of potential energy, this is related to the gravitational constant times the geometric height, z, and the atmospheric transport of kinetic energy, and this is closely related to the wind speed. So these 3 added together are this pink line that we see through here, from the southern hemisphere to the northern hemisphere. The atmospheric transport of latent heat is given by the light blue or teal line that we see depicted here, as I'm tracing it out with my laser pointer. And then finally, the oceanic transport of sensible heat is given by this orange line that we see depicted through here. So we're not necessarily breaking this down into those transient, stationary, and mean terms as we introduced on the previous slide, but rather to the physical constituents associated with the energy or heat budget. Mean, eddy, and stationary transports comprise each of these terms that we see here. So if we orient ourselves with the total energy transport here, it passes through 0 right at the equator, and it has positive values in the northern hemisphere and has negative values in the southern hemisphere. They peak around 40 to 50 degrees north latitude in the north hemisphere and 30 to 40 degrees south latitude in the southern hemisphere. Because of the convention here, these positive values are denoting transport from the equator toward the poles, or more generally northward in the northern hemisphere, and from the equator toward the South Pole in the southern hemisphere, or more generally southward. So in the total, energy transport is from the equator toward the poles in both hemispheres. We see that the pink and orange lines have a very similar structure with weaker magnitudes to that total energy transport, and some variability from one latitude to the next. But in general, the oceanic transport is poleward in both hemispheres, and the atmospheric transport of sensible, potential, and kinetic energy is poleward in both hemispheres, although it is displaced slightly off of the equator in the northern hemisphere. So there is some depiction of southward transport between about 5 north and the equator here within the northern hemisphere. And this is associated with the Hadley cell. On average, the center location of its ascent typically skews ever so slightly north of the equator in the annual average. But the latent heat transport by the atmosphere is quite a bit different from those other two. It too crosses zero off of the equator, roughly at the same place as the sensible kinetic and potential energy term does. However, it is negative here in the northern hemisphere and positive here in the southern hemisphere. So this is indicating latent heat transport toward the equator, or more specifically toward 5 north here, and toward 5 north, or from higher latitudes toward the equator in the southern hemisphere as well. This term is associated with water vapor transport. In the tropics, you have a net precipitation, which is associated with condensation, losing vapor to precipitation in some fashion that then falls out. This water vapor is replenished by this transport of latent heat associated with water vapor from higher latitudes toward the polar regions. This is also largely accomplished by the Hadley circulation within the tropics, from the subtropics to the tropics. So now we want to go on to a slightly different concept, and this is that of absolute angular momentum. So the absolute angular momentum is defined mathematically as m equals two separate terms here. This first one here, a times cosine of theta, is the distance from the axis of rotation. So we have this cartoon schematic of the Earth over here at left, and the axis of rotation is this black line that goes straight up and down through the north and the south poles. So the Earth rotates around that axis. This a times cosine of theta, where a is Earth's radius and theta is latitude, is the distance at the surface of the Earth from that axis of rotation. So at the equator, where the latitude is 0, cosine of theta would be 1, and the distance is just equal to Earth's radius, or 6,780 kilometers. Whereas up here at 30 degrees north latitude, it's not the radius of the Earth, so from there to the center of the Earth, but rather from there to that axis of rotation still at 30 degrees north latitude. And because the Earth curves as you go from the equator toward the poles, that distance approaches 0 as you go from the equator, where it has its maximum value, towards 0 at the north or at the south pole. So a times cosine of theta at 30 north would be 5,500 kilometers, so about 1,200, 1,250 kilometers less than it was at the equator, and it continues to get smaller as you go northward from there. This other term is the rotational velocity, and it includes two components. This omega times a times cosine of theta is Earth's angular velocity, and it too depends upon the radius of the Earth and the latitude, where this omega here is Earth's rotation rate, 7.292 times 10 to the minus 5th radians per second. Then we have this zonal wind, U, that we see here, and that is what we typically would associate it with, the east-west wind here on the Earth. So the multiplication of these terms together, omega a squared cosine squared theta plus a times u times cosine of theta defines the absolute angular momentum. Even if an air parcel is initially at rest, even if 0 or u is 0 initially, m is not 0 so long as you're not at the pole where theta would be 0, or sorry, cosine of theta would be 0. M is non-zero by virtue of the Earth's rotation. So the Earth rotating around means that even an initially at rest air parcel still has some amount of absolute angular momentum with it. So in the absence of friction, whether that be with the surface or with other air parcels, when you move with the wind, the absolute angular momentum does not change. It is what we would call conserved. And so this depiction here at left is taking into account the hypothetical scenario of an air parcel in the upper troposphere that has reached near the tropopause at the equator in the ascending branch of the Hadley circulation that is now going to move poleward away from there toward higher latitudes. So we want to consider what that means in this absolute angular momentum context. So we're going to consider that poleward branch with no initial zonal wind, and of course being at the equator, cosine of theta equals 1. So our equation for m becomes a times omega a, or omega a squared, and that is equal to 2.96 times 10 to the 9th meters squared per second. So a very large value. So if we say that this does not change following the wind or following the motion, as this air parcel reaches the tropopause here near the equator and wants to be directed poleward from there, whether that be to the north or to the south in either hemisphere, this value of m is not going to change. But the latitude is changing. So some of the constituents of m, that cosine of theta term, is no longer going to be 1, but rather it's going to be less than 1. So because those terms are going to get smaller, u has to get larger. The zonal wind has to become non-zero, and in particular it has to become positive in order for m to stay the same. So if we do this, we would find that you would get a zonal wind that is very, very large, over 100 meters per second, much larger than we actually observe, just by virtue of taking an air parcel from the equator near the tropopause and directing it poleward toward 30 degrees north latitude or 30 degrees south latitude. So we can plug in different values of latitude and solve for the u wind because we know what the absolute angular momentum should be due to its conservation. That acceleration of u from west to east, or westerly wind, it results in the subtropical jet stream aloft. So these subtropical jets in the annual average and the longitudinal average are centered roughly around 30 degrees south and 30 degrees north latitude. An air parcel moving from the equator to either of those under the conservation of absolute angular momentum would accelerate to 134 meters per second. That's on the order of about, not quite 300, somewhere in the ballpark of 300 miles per hour. That's much, much larger than what we actually observe, which is more on the order of 20 to 30, maybe 40 meters per second. So there is some loss of angular momentum as air parcels go from the equator toward higher latitudes in the poleward branch of the Hadley Cell circulation. There is internal friction associated with turbulence, like the clear air turbulence that you might have experienced in an aircraft. And then you also lose absolute angular momentum to the mid-latitudes as this jet no longer is just a coherent, long feature, but rather breaks down into waves that are typically associated with cyclones along that initial jet axis. So this conservation of absolute angular momentum can't be used directly to assess how fast the subtropical jet should be, but rather does tell us that there should be a westerly jet that develops as an air parcel moves poleward from the equator in either hemisphere, with other terms that ultimately affect just how strong it can actually be. We've looked at this in a global average perspective, but when we get to features that are more local variability within the tropics, such as the Madden-Julian Oscillation or even El Niño Southern Oscillation, we'll see that the heating, the ascending branch of the Hadley Cell, is stronger in specified locations than it is elsewhere, so that global average is not true at any particular location. So we'll see that this subtropical jet originates from preferred locations, generally where that ascending branch of the Hadley Cell is strongest, such that the poleward branch is also particularly strong, and these air parcels have a greater impetus to move poleward from the equator. So finally, we want to take a look at some measures of variability with the Hadley Cell. And though we've already taken a look at this on previous slides, especially with our tropical climatology lectures, it bears repeating here as well. So our discussion to this point has largely focused on the annually averaged structure of the Hadley Cell. So from a radiation perspective, that's when the radiation is maximized at the equator and becomes smaller north and south from there. However, because of the changing tilt of the Earth through the seasons, we know that radiation is not always maximized right at the equator. It's always maximized in whichever hemisphere is in summer. Northern Hemisphere, June, July, August. Southern Hemisphere, December, January, February, from a meteorological perspective. So consequently, it is typically warmer in the summer hemisphere, and the ascending branch of the Hadley cell becomes concentrated in that summer hemisphere. So in this case, January, February, March, Southern Hemisphere's second and third months of summer and transition to fall, you have negative values of this vertical motion indicating ascent, here concentrated between the equator and 15 to 20 degrees south latitude. Conversely, descent is concentrated in the winter hemisphere where it is relatively cold. And we see that here in the northern hemisphere for January, February, and March, our second and third months of winter and our transition month into spring. Likewise, the pattern flips as you head to northern hemisphere summer. July, August, and then toward fall in September, ascent is maximized in the northern hemisphere between the equator and about 15 degrees north latitude. Descent is maximized in the southern hemisphere between 5 south and 30 south through these months as well. So the leading mode of variability with the Hadley cell is that associated with the seasons. However, land-sea contrasts also facilitate Hadley cell variability. So the most common manifestation of this is monsoons. Elevated land masses such as the Tibetan Plateau in India over toward Southeast Asia. You also see this in Central and Southern America for both northern and southern hemispheres, and to a lesser extent in Africa as well. So we get these heating-driven monsoon circulations that cause a concentration of ascending motion to be found off of the equator in each hemisphere over land, whereas over water you'd see a comparative minimum in rising motion associated with that. And this is partially driven by the variability in how quickly heat or land responds to an amount of heating as compared to water. There's also some variability in water temperatures near to the equator within the tropics that we haven't yet gotten into, but we'll see become important when we start to talk about the Walker circulation and El Nino in coming weeks. So oftentimes the climatological state is warmer waters in the western portion of a basin and cooler waters in the eastern portion of a basin near to the equator and in the tropics more generally. So where it is warmest tends to be where the ascent is maximized. There's all different time scales, all different forms of variability in that structure, however, and that's really what the next several weeks of our course material will focus on, is variability in that structure. But for now, this concludes our discussion of the Hadley cell circulation.